In January 1984, a national radio station deliberately broadcasted minutes of piercing, destructive static to millions of listeners across a country. To a casual listener surfing the dial, it sounded like a catastrophic transmitter malfunction or a broken signal. But it wasn't an emergency, and it wasn't an accident. If you happened to connect an ordinary audio cassette deck to that radio, hit the record button, and then patch that recorded tape into a home-built computer, something unexpected happened. That screeching noise transformed. It decoded into an interactive video game, a mathematical calculator, or an educational program. Decades before the modern internet, app stores or Wi-Fi became household realities. An isolated population discovered how to download software directly through standard public radio waves. It sounds like a modern myth, a futuristic concept completely misplaced in time. But this wasn't a high-tech corporate experiment. It was a desperate, brilliant engineering hack designed to defeat an economic blockade. To understand how this system even became possible, we have to look closely at a unique technological bottleneck in the early 1980s. The personal computer revolution was exploding across the Western world. Machines like the Apple II, the Commodore 64, and the Sinclair ZX Spectrum were beginning to reshape homes, classrooms, and offices, fundamentally changing how human beings interacted with data. But for millions of people living inside the borders of Yugoslavia, these machines might as well have existed on another planet. The country was navigating a severe economic crisis. To prevent foreign currency from draining out of the domestic economy, the government enacted strict import laws. Any foreign product costing more than a small, tightly controlled allowance was heavily restricted, requiring nearly unobtainable government permits. Computers were officially classified as luxury items, meaning you couldn't simply walk into a store, and you couldn't legally order one from abroad. Customs officials would routinely seize components at the border. An entire generation of students, hobbyists, and engineers found themselves completely locked out of the digital age. But history shows that when you cut off a highly educated, passionate population from a tool they desperately want, they don't give up. They look for a back door. That back door was found by an independent engineer named Voja Antonić. In the summer of 1983, while on vacation, Antonić wasn't relaxing. He was studying the technical manuals of early microprocessors. As he analyzed the schematics of popular Western computer designs, he noticed a distinct pattern that he found fundamentally flawed for his situation. Machines like the Commodore 64 or the Atari 800 relied on a complex array of specialized, expensive coprocessors. They had separate chips dedicated entirely to handling graphics, generating sound, and managing memory. This specialized silicon drove up the cost, required complex manufacturing, and made the machines impossible to replicate with locally available parts. Antonić asked a fundamental engineering question. What if you stripped away all those specialized chips entirely? What if you forced the main processor to do absolutely everything through clever programming alone? His goal wasn't to compete with Western tech giants on raw processing speed or high-end graphics. He wanted to design a machine so simple, so completely minimalist, that anyone could build it on their kitchen table using standard, low-cost components found in local electronics shops or salvaged from old television sets. His solution was a machine called the Galaksija, and its architecture was a masterclass in extreme minimalist engineering. To eliminate the cost and scarcity of a dedicated graphics chip, Antonić made a radical design trade-off. He programmed the main CPU, a standard, widely available Z80 processor running at just over 3 MHz, to generate the video signal directly for an ordinary television screen. Think about what that actually means in practice. The CPU had to work double duty, constantly alternating between two completely different tasks. It had to execute user commands and game logic, but it also had to handle the brutal, unforgiving timing loops required to draw individual pixels on a cathode ray tube screen. The processor had to send a synchronization pulse to the television down to the exact microsecond. If the computer's software code slipped or miscalculated by even a fraction of a second, the image on the screen would instantly distort, flicker, or completely collapse. This put an incredible burden on the software design. The base model of the Galaxia possessed just 4 kilobytes of random access memory. To put that in perspective, that is barely enough memory to hold a single page of plain text today. Yet, by writing highly optimized machine code where every single byte served multiple functions, Antonić managed to fit a complete operating system, a video generation routine, and a programming language interpreter into that tiny space. Rather than patenting this breakthrough to make a fortune, he shared the full schematics in a popular science magazine, giving the blueprints away to the public for free. But building the computer was only half the battle. A computer without software is just an expensive, silent block of electronics. In the West, software distribution relied on commercial infrastructure. You drove to a computer store and bought a floppy disk or a pre-recorded cassette tape. In Yugoslavia, those stores simply did not exist. There were no software publishers, no distribution networks, and no physical supply chains. This is where the project took a radically unconventional turn, leading to a system that felt completely unique on a global scale. The magazine's editors, along with a prominent late-night radio host named Zoran Modli, realized something critical about how early computers stored data. Computers saved programs onto cassettes by converting binary code, ones and zeros, into distinct audio frequencies. A high-pitched tone represented a digital one, and a low-pitched tone represented a zero. They reasoned that if a consumer cassette player could feed these audible frequencies into a computer's microphone port, then a radio station could broadcast those exact same audio tones over the national airwaves, allowing thousands of people to record them simultaneously. When Zoran Modli stood in his broadcast studio to attempt this experiment, the process required exact precision. It wasn't a perfect, flawless system. If there was too much atmospheric static on the radio frequency, the signal would degrade. If a family member turned on a kitchen appliance, a minor voltage surge could introduce noise into the recording tape. If the listener's tape recorder heads were slightly dirty or misaligned, or if the volume level on the receiver was a fraction too high or too low, the data would become corrupted. The Galaksija would read a checksum error, print a loading failure on the television screen, and the user would be left with completely useless data, forcing them to wait until the next week's broadcast to try recording it again. But when the signal-to-noise ratio was just right, the system worked perfectly. The listener could take that freshly recorded tape, hit play, and watch code compile into a working program. They had bypassed physical distribution networks entirely using standard FM radio infrastructure. The real-world impact of this experiment completely blindsided its creators. The magazine editors initially estimated that perhaps a few hundred hardcore hobbyists would take the trouble to source the parts and solder the computer together. Instead, over 8,000 people successfully assembled their own Galaxia units. A massive, completely decentralized user community emerged overnight. Families would gather around their radios late at night, carefully adjusting their tuning dials like safecrackers to ensure the cleanest possible audio signal. Soon, this system evolved into a highly organic two-way ecosystem. Users weren't just passively consuming the software being broadcasted to them. They began writing their own custom programs, creating original video games, and debugging math software. They would mail their physical cassette tapes back to the radio station, and Zoran Modli would broadcast those user-created programs back out to the rest of the country. Long before the modern internet popularized the concepts of open-source software, crowdsourced development, and peer-to-peer networks, this community had established a fully functional digital network using nothing but analog radio waves, basic soldering skills, and consumer audio tape decks. Despite its engineering brilliance and massive cultural success, this unique broadcast computing model did not survive into the next decade. Its decline wasn't due to a technical flaw in the concept, but rather the unstoppable progression of global economic and market forces. By the late 1980s, Yugoslavia's economic restrictions began to ease, and the global cost of manufacturing silicon dropped dramatically. Mass-produced Western computers, like the Commodore 64 and early IBM-compatible PC clones, finally became readily accessible and affordable. These new machines offered full-color graphics, dedicated sound chips, and massive commercial software libraries that a home-built 4-kilobyte computer simply could not compete with. Furthermore, physical storage media became incredibly cheap, and the eventual rise of telephone-based dial-up networks provided a reliable, interactive two-way data stream that rendered one-way radio data broadcasts completely obsolete. The Galaxia gradually faded into technological history, preserved mostly in technical museums, and by a small community of retro computing enthusiasts. The story of the Galaxia and its radio broadcasted software demonstrates that the evolution of technology is rarely a straight, predictable line. We often view our current world of seamless wireless updates, app stores, and cloud computing as the inevitable outcome of Western corporate innovation. But decades ago, out of absolute material scarcity, an isolated community proved that an entirely alternative technological path was possible. They built a decentralized software network using tools that were already sitting in every citizen's living room. It changes how we think about human progress. It proves that innovation isn't just about having access to the most advanced laboratory, the clean rooms of Silicon Valley, or the highest research budget. True engineering is about recognizing the unseen potential in existing infrastructure and finding the most elegant, unexpected solution using the exact tools you already have.